Stepney, Professor of Computer Science at the University of York, Fellow of the British Computer Society, and Director of the York Centre for Complex Systems Analysis. Often you find that computer scientists start out life in some other academic career, especially in theoretical computer science. But Susan is surely distinctive in this respect. She started out as an astrophysicist. She took her undergraduate and graduate degrees at Cambridge, where she was awarded the Tyson Medal and the Raleigh Prize, both prestigious prizes awarded to notable and distinguished British mathematicians and astronomers. And then, of course, she won a college research fellowship and postdoctoral fellowship. But she turned her back on the academic world and headed to Marconi as a research scientist, and then to Logica as a consultant there. But then the lure of the lofty questions took her back to York, where she has characteristically diverse interests within theoretical computer science. Complex systems, non-standard computation, artificial biology, the list goes on. I must say it's a particular pleasure for me to introduce Susan, because I knew her when she was an astrophysicist. And I was thinking about those times, and two things stuck out to me. One was how we used to, with others, as students do, argue about lofty topics. Okay? And here we are, arguing about lofty topics. But the other thing was that I remember my attempts, and this was only for word processing, to use the Cambridge mainframe, and how it was temperamental, to say the least.
I remember it well.
How you managed, I don't know. But the gap between then and now, yes. Okay, so Susan.
Thank you very much. Okay, so no astrophysics in this, except a little bit about the universe, but I'll come on to that later. So, yes, so the title, When Does a Slime Mould Compute? I'm afraid this has probably got very little to do with Ada Lovelace, but there's, you can just about squeeze it into questions of computation.
There's some argument that Lord Byron was slimy. Yeah.
That works, I'll go with that. Okay. So, talking about slime moulds computing, if I say the word computer, most people will think of these kind of things, although I notice around the room that there's enough people who probably think of this kind of thing. Yeah. And there might even be one or two who think of this kind of thing.
In this room, yes.
Yes. Normally, if I'm talking to students, they're probably not even sure what some of these other ones are. But do you think of these kind of things? So this is a picture here of some slime mould growing over... usually it's oat flakes, but these look more like small pieces of pizza. Dynamical systems. This is a group of tiny little crabs that were persuaded to compute a logical gate. And this is a picture of a black hole. Right past stays with me. But also, you might think of these kind of things if you're stretching the idea of what might be a computer. We've got Stonehenge, which is potentially one of the earliest computers to do with looking at astronomical events. We have, I'm not sure how it's pronounced. I've never heard anyone else say it. I pronounce it Antikythera, but that might not be right. But this definitely is a computer, obviously engineered with gears and so on. And this is an orrery. But those aren't the kind of computers we think about nowadays. Some people have even claimed that these kind of things might be computers, sometimes not necessarily entirely seriously, all the way from a rock to the entire universe. So I promised you the universe would come up, and I will mention it again later. So, in order to answer the question, what are these computers, what are they computing, we really do need to drill down into what is it actually that is a computer. So what does it mean to say that some physical system of interest is running a computation, is computing, rather than simply being a physical system doing its own thing? So the question really is, when does a physical system compute? And here slime mould is an example of a physical system that some people have used to perform what they call computations. But we've also got this thing, is this bouncing ball computing parabolas or what? So we need to think about what this question means. So I'm going to go through 3 steps along the way. First of all, to explain what science is, then to explain what engineering is, and then to explain what computing is. So it might take some time. Okay.
I would call life, the universe, and everything, right?
Indeed. Okay, so starting off with science. obviously this is highly simplified in order to make the point. So, but we have a physical system here, pendulum, and that physical system scientifically gets represented as some kind of abstract model. So we have the pendulum equation. Now obviously this abstract model has abstracted away a lot of the details of the physical system, but also an abstract model can be instantiated into a physical system that has the required properties. And we're quite used to instantiating abstract models into lots of different physical systems. If we actually had the linear equation here rather than this nonlinear one, it would just be the simple harmonic equation, simple harmonic motion equation, and you might abstract it into a pendulum, or you might abstract it into an electric circuit, or instantiate it, sorry, into an electric circuit. But the point here is we have two very different kinds of systems. We have a physical system, and we have an abstract model. So when we're doing science, in a very simplified way, we start off with some physical system. Here maybe some ice in heat, and time goes by and the physical system evolves it does what it does. And then we finish up with the physical system in a new state. Here the ice has melted. And so when we're doing science, what we might do is we represent the physical system in some abstract model, some model of the physical system. And then we might have some idea, some theory about what it does, and we can use that to infer in the abstract level what will happen to the physical system. So we have a later state of the physical system, and we've inferred what happens. Then we can say, well, okay, that's our inference of what happened, what actually happened. So we can now represent the final state of our physical system abstractly. And then what we're interested in is the difference between those two, the actual after state and the inferred after state. And we're interested in the difference. And what we want is a good theory, and a good theory is one where that difference, that epsilon, is small as is needed for the theory, small enough. And if epsilon is too large, if the difference between what we've inferred and what we observe is too big, then we have to change the theory. So in science, reality trumps theory. I told you this is a slightly simplified version of science, but in my abstracted version of science. And so the theory is a model of reality, and we've got to remember that models are always approximations. So here's an example of that approximation of melting water breaking down. If we get too hot, it turns into steam, and that wasn't necessarily in our model. So, and we've got to realise these approximations always break down outside the model's valid domain. But the point about a good theory is it allows you to predict what's happening in the physical system without needing to run the physical system. So you don't need a reality check every time that you infer, once you've got a good enough system, provided you stay within the domain where those approximations hold. So this is the thing here. So now we've said epsilon is small enough that these two things are close enough together that we've got a good enough theory. And then what we can do is, instead of time going by, we can predict what the final state of the system is going to be. That's science. So the definition of science, from my point of view, is we have an abstract dynamic C. This is the inference we were doing, our theory of a well-characterized physical system. That means our theory is good enough, we actually understand it, and we can use that theory to infer the physical dynamics H, subject to some representation, because obviously there's always, I'm glossing over those complications. So that's science, and I want to have that model there because I want to contrast it with engineering and use it to say when some things are computing and others aren't. So let's move on to engineering or technology. Again, we've got a physical system here. It's usually an artifact now because it's an engineered artifact. And we have an abstract model, some engineering model. And the physical artifact is represented by the model, and the model can be instantiated in the physical artifact. And so here, physical system, a bridge, an engineering model. This isn't the engineering model of this bridge. These are just pictures off Google in the usual way. So what do we do when we're doing engineering as opposed to doing science? So what we have here, now we have an abstract model. And you remember when I was showing you the science picture, I started at the physical level. Started with the physical system and we were trying to find the model. With engineering, we start with the model, we start with what we want, and then we can use our understanding of the physical system to infer that our abstract system behaves the way we want, that if this is an abstract model of a bridge, that the bridge doesn't break under load and those kind of things. And then what we can do is we can instantiate our abstract model in some physical artifact. And then the physical artifact, people go by, over the bridge, has a final state, and then we can represent the final state of the bridge. And again, there's potentially a difference between the inferred final state and the actual final state, physical final state. And what we want in engineering is for epsilon to be small enough so that we've got a good bridge. The bridge I was actually showing you was the Millennium Bridge across the Thames in London, which wasn't a particularly good instantiation of the model because it wobbled when people walked over it, rather a fundamental problem. So a good instantiation makes epsilon small enough. But the fundamental difference between science and engineering is when epsilon isn't small enough, epsilon is too large. It's the physical system that needs to be changed in engineering. The desired model trumps reality. So if my model and reality are different, I've instantiated the model incorrectly, or I've got some incorrect instantiation, some incorrect bridge going on. So I have to change reality. I have to re-engineer the bridge. In this case, I think they hung some weights on it to stop the resonances. So again, even in engineering, a theory is a model of reality, and it's always an approximation. So here we see exciting failure mode of a bridge. I'm glad I wasn't around when this was happening. But again, you could put a sign up in front of the bridge giving a weight load to tell you what the domain of validity of your approximation is. And a good instantiation of the bridge allows you to use it without needing a theory check. I don't need every time I get up to a bridge to run my little calculation to check that I can go over the bridge. Provided I'm within the domain of approximations, I know because I've got a good theory that I can go over the bridge. So looking at this again, we have our loop, and again the difference is here we started at the top and we moved down. And before I said we could predict what was going on here, but the difference with engineering, with a well-engineered technology, is in fact we can predict what's going on up here. So that's the difference between science and engineering, is what we predict.
I don't know if it matters, but maybe in engineering something with the theory is wrong. The instantiation is perfect.
Yeah, I glossed over that and I said with a well-characterised theory, so I'm assuming that the theory is right. But that's a very important point and we'll be coming on to that later.
Since you had one interruption, you haven't allowed for the case that the theory might cover a huge variety of cases because the theory embodied something like a grammar, and then you can have any number of predictions satisfied and still not know whether your theory is right or wrong. That's Chomsky's point.
Yes. I mean, there's lots of philosophy of science and stuff
there.
Yes. And I'm glossing over all that because I'm just trying to draw some analogies. But yes. So a lot more of this is addressed in the paper, but obviously
I don't quite understand the last change. You said you're not doing analysis, you're doing a prediction. I don't quite understand the difference between.
Right. Well, the prediction means that I don't have to do the inference. I can just walk around this way. And I don't have to predict every time that my final state is going to be okay. It is because of the fact that it's a well-engineered system.
And that fact is known.
And that fact, is known as well as can be known, yes. And that's why I said if the epsilon was too big, it's the reality that's wrong, you have to go and re-engineer the system. Okay. So I've talked about this inferring at the top level. So what is doing the inferring? So a long, complicated calculation may be done with pencil and paper and a brain, or with a computer. So we finally got around to using the word computer. So a computer is a case of engineering. In this, a computer running a program is a case of engineering. So a computer is a physical artifact, and it can be used to represent a computation. So it's put in a particular state to represent the computation. And a computation can be instantiated in a computer. So it's computation. So there's an abstract model and there's a physical artifact. And it's just like the engineering side. We start with some kind of abstract model that we're interested in and some computation that we desire to do. And what we can do, and this is the same diagram as the engineering diagram, we can instantiate that model in a computer, which normally we don't bother thinking about engineering the device because we just gone and bought one of those, but of course it has to be done. Normally we just think about programming, encoding the input, putting the device in the right initial state. And then the laws of physics happen. Time goes by, the computer has a final state, and then we decode the output and back into our abstract model. And again, we are interested in the difference between the computation we desire and the computation the computer has computed. And again, we want epsilon to be small. Sorry? Yep.
Yeah. So just to be sure, so computation for you is an abstract mapping or something like this?
Yeah. So I'm at this point, I'm not at all talking about what's possible to do here under what conditions. I'm just saying this is what we want to do. It might not be possible because it might be uncomputable or something.
Right, but it's an abstract mapping or something.
Yeah. So I'm using computation to mean the abstract mapping and computing to mean the physical execution of that abstract mapping. But
okay,
you can use what words you like. For,
just
yeah.
what it used to be.
Yeah. Okay. So that epsilon is still there, and so a good instantiated computer makes epsilon small enough. And what we call it, if it's not small enough, we call it a bug. And so the physical device needs to be changed. Usually that doesn't mean actually changing the physical device, it usually means changing its initial state. But that is still, in a sense, a change of the physical device. But when we come on to non-standard computing, it can also mean changing the physical device. But again, the desired computation trumps reality. If the computer has a bug in it, the computer's wrong, and needs to be debugged. But again, this theory is a model of the reality. Computers can still have things that are happening outside the domain of validity. And for example, no computer can implement a Turing machine because it can't implement the unbounded memory. So you can always get these out of memory issues. And the approximations break down, and so we have to stay within the domain of validity. But the point is, a well-instantiated computer, that is a well-engineered physical device with a well-debugged program, allows the use without needing some computation check every time the system's used. So if we go back to this picture, and now we're saying epsilon is small enough that these are sufficiently close, then we don't have to do the inference. We can use this system to predict. In other words, we're doing that inference, that computation, via this computing loop. And so this is what physical computation means. It means instantiation, physical evolution, and decoding. Okay, and I'll show how that works in a variety of cases. But that's our definition now. Computation, I should actually say computing. I'm not very consistent with distinguishing computation. Computing is using the physical dynamics of a well-engineered physical system to predict an abstract dynamics. And the point here, for non-standard computing anyway, is unconventional computing, is there's nothing in that definition that says the computer has to be one of these kind of things. It can be anything that fits into that framework.
Could you show it just a little longer, the definition?
Oh, the definition. I can let you have the slides after if you want, and it's in the paper that I'll reference at the end as well. Yeah. Okay. So it's using the physical dynamics of the system to predict an abstract dynamics. Okay. But as I say, there's nothing that says that physical system has to be what you think a computer might be. It doesn't have to be silicon, it doesn't have to do conventional kinds of computation. obviously with the Ada Lovelace theme, we can say it doesn't have to be silicon, it can be brass gears at least. So I managed to get something in about that. Okay, that'll be it. But we can use this definition to understand how unconventional systems might be doing computation, might be computing. So here's an example, again, pandering to the audience. I usually have a younger audience who have no idea what one of these things is. But so this is using wooden sticks to do computing. Actually, my slide rule was plastic, but wooden sticks will do. So the calculation we want to do is a multiplication. The theory of how the system works is that if you add two lengths together, you get the sum of those two lengths. The instantiation, we instantiate abstract numbers as physical lengths on the wooden sticks, and in the real world we slide the things about to join the two lengths together, and then the output, the decoding, is reading off this, and because this well-engineered device has been engineered with a logarithmic scale, that addition turns into a multiplication. So that's how the slide rule computes. Obviously not universal, but it can multiply, and various other bits and pieces. So slime mould. So this was in the title, so I have to talk about slime mould. How might a slime mould be computing? Well, okay, the calculation, one of the things that they've been used to do is to solve mazes. So here's a little example. Solve a maze. So the theory is how a slime mould behaves in the presence of food. And the theory says that in the presence of food, the slime moulds minimise the distance. So a slime mould is it's actually a single-celled creature, this particular slime mould, but it's quite a large single-celled creature. And what it does is it can put parts of itself in different places, and it tries to put parts of itself on food, but it wants to stay in one thing. So if there's a piece of food there and a piece of food there, it wants a bit of itself on that food, a bit of itself on that food, and then the rest of itself in between. And the idea is that it doesn't want much of itself in between, it wants most of itself on the food, and so it minimises the distance in between. So the instantiation, you get a slime mould and you chop it up and you sprinkle it over the maze, and then you put some water on it to make it all glue itself back together again. It's amazing what these biology can do. And what you do is you put a food source on the entrance and the exit, and it's usually, as I said, a little oat flake. It's not that it eats oats, apparently it eats either the bacteria or the mould that grow on oats, but it's a food source for it. So there's a food source here and a food source at the exit, and in the real world, time passes, and the slime mould, which was initially over the entire maze, contracts into a shortest path. So you can see this is the initial, here's an intermediate stage where it hasn't quite finished, and here's the final stage, or a near final stage. And the output, you read off the path taken by the slime mould. So it kind of fits into the model, okay? And so there's a shortest path here. There are some caveats, and I'll come onto those in a bit. I heard an intake of breath as if there was
just curious. Do we know if you make so we can solve this kind of maze problems in time that is linear in the size of the graph. If you make these things bigger and bigger, how does the slime mold? Is it linear or quadratic algorithm?
I'm coming on to that. It's worse than that. It's not whether it's linear or cubic, or it's whether it actually solves the problem or not. But I'm coming on to that. Yeah. So they do other ones, and so there are other sort of minimum spanning tree problems it can do, and various other bits and pieces. People have a lot of fun doing this kind of stuff.
It's got a built-in failure detector which cuts in too soon.
Which is, it dies.
No, if it's gone on for long, it hasn't found it.
Right. Okay. Yes.
So
no, the real problem is actually if you don't give it enough food, it gets up and walks off.
That may be an implementation.
Yes.
So if you don't give a computer electricity,
it doesn't walk off trying to find some electricity. It just sits there sullenly.
So if there are two equal paths, will it use both, or does it should?
I'll come on to that because
Okay.
it's okay, so having got a definition of computing, we can now use it to answer the questions of whether something is or is not computing. So here's an example. all heard of the clock paradox of a broken clock's right twice a day, whereas a clock that's 5 minutes slow is never right. Well, this shows why that argument doesn't work. So if we were trying to use a broken clock as a computer, or trying to use a clock as a computer, we can think of a clock as a computer that computes the elapsed time. We have some abstract model and we're wanting abstractly to find out the time afterwards given the time before, after some time has passed. And so what we would do is program encode the input, we would set the clock to the right time, and then we would let it run. And a working clock would run and we would then decode the output and read off the time. But of course a stopped clock doesn't. It says the same time at the beginning. And so the problem here is there is no way we can decode the output on the stopped clock except by using another clock. So this idea that it's right twice a day, the only way that you can know when it's right and therefore use it as a clock is to have another clock, which kind of defeats the object. It's a bit of a cheat.
Yeah, so we can say that a broken clock doesn't compute the time, but can't we use it to compute the identity function, for instance?
We can. It's a very complicated way of computing the identity function, but when we're using the clock in the clock paradox of saying it's right twice a day, we're using it to compute the time of, and we're saying at this time it's giving us the right answer, and on all the other times it's giving us the wrong answer. The only way we can know when it's giving the right answer is to use another clock to do the computation.
That's kind of to say that you need to give it, for it to compute the answer, you need to give it the answer.
Yeah.
But that, that's perfectly legitimate in like a Turing machine that has the answer on its tape, any finite string. This is the standard proof that a Turing machine can compute any finite sequence. You give it the answer first. So I don't see having to use the secondary clock shows that computation is not
well, it shows that this clock is not doing the computation, that there's more to this computing system. Because, in fact, what's happening is all the computation is happening there.
Yes, you don't say that about the Turing machine with the finite sequence, though. That very machine is computing that sequence, but, someone else wrote it on the tape to start with.
To start with.
To the other clock.
To start with. This is to end with.
That's true.
And it
You
didn't
haven't
break.
mentioned the time.
Yeah.
The mechanism to scan didn't
Discussions this afternoon,
This
yeah.
particular argument with Scott Aronson makes me think we should leave this for the Q&A this afternoon.
Okay. And I'll be at a disadvantage because I didn't hear Scott's talk, but never mind. But the point is that this system is insufficient. You need more in the system. You can't instantiate the system. You have to wait until is this clock telling the right time? The only way I can tell is with a separate clock afterwards. So this system, the dual clock system, yeah, fine, but then you're not using the broken clock. However, the other half of the argument that says a clock that's 5 minutes slow is never right is also wrong by this argument. Because there, let's go back, here we encode it with a 5 minute slow clock. Time goes by, shows the time, and then we decode it and add 5 minutes. The decoding process adds 5 minutes. That's a fixed, predefined decoding to add 5 minutes. So the 5 minute slow clock is telling the right time with the extra decoding. And this is the important point, that the computing isn't just done here. There can be computing needed here, and there can be computing needed here in the encode and decode part. And very often in systems where people say, wow, this system can do computation that a Turing computer can't do, there's often a lot of hidden computation going on in the encoding, the setting the system up, and the decoding, the reading the answer out of the system. Whereas people tend to just analyse this part of the system.
But it opens up. I can use a broken clock now to compute every computable function, right?
Okay.
I'll set up the input on the clock. It will do nothing, and I'll do all the computation that I want in the decoding. My decoding function will do. I want to compute the hypertangent, right?
Okay, so that's Putnam's rock. Thank you. I didn't plant that question. but it was very nice. It's the exact problem with Putnam's rock, which says that a rock computes because you can do everything in the answer. And the problem is, the only way you can work out what that decoding is to have done the computation some other way. It's not the rock doing the compute, it's the other computer that you use to set up the decoding that's doing the computing. And the problem is, again, is working out what is the system. So if you're trying to say it's the rock doing it, well, it's not the rock doing it because you've had to do a lot of work to set up the decoding. Not only that, you have to put that decoding in after when you know what the answer is that you want. It's not a predefined decoding. And it's all being done.
No, so a rock is a little too simple because
it's exactly the problem. It's Putnam's rock.
I want to go back to the clock because the clock I can clearly set up. Set up a number, an input number.
Yeah.
It will do nothing.
Yeah.
But then I will just do the computation that I want in the decoding.
It's exactly the same problem. A broken clock is a rock. It does nothing.
No, it's not a rock. I can set it up. Let's assume that it's.
I can
turn this stone over.
Yeah.
You can turn the stone the way you want first.
Then it's the same thing.
Yeah. But it's exactly Putnam's rock problem of where the computation is happening, and in that case, it's all. Well, okay, I'm trying to map the microstates of the rock to my answer through some mapping function. That mapping function is post hoc and has been computed somewhere else. And that's where the computation is happening, not in the rock. And that's the important part, is the fact that you need to consider all three sides of the loop, whatever, in order to figure out where the computation is happening. It's not just happening in the physical system. Okay, so we also have the other extreme. Some people claim that the entire universe is computing itself, and that everything just computes itself, which is an extremely useless definition of computing because it doesn't distinguish computing from physics in that case. So how would the universe computing itself fit into this model? So we'd have to start with some abstract model. We'd then have to instantiate the universe, let the universe run, and then we'd have to decode the output. Now this is a different problem. Here, in this case, we don't have an abstract model that we've used to instantiate the universe. We've only really got the stuff at the bottom. Now, we can, of course, look at the beginning and look at the end, but that's doing science. If we start with a physical thing and try and have a model and then use that to predict what the universe is going to do, that's predicting what the universe is doing, that's not using the universe to compute.
Also looking at it's changing the universe.
There are lots of subtleties like that, yes. I'm standing outside the universe.
Yes, okay.
Okay, fine. Okay, so the problem, there's no abstract model in a computational sense, and there's no representation going on in the physical one, and so there's no computation happening there. And then this one's more like the kind of slime mould idea, only I've used spaghetti to show what's going on. So this is a spaghetti computer, allegedly. So here we've got an ill-characterized substrate. We have no theory of spaghetti. Okay. So we'd start with our abstract model and we'd instantiate our spaghetti somehow, and time would go by and the spaghetti would do whatever spaghetti does. Maybe it moves around for some reason. And then we have to decode the output. Now the problem here, the reason why we can't say that this is computing, is because actually we have no well-characterized theory. We don't know what the spaghetti or this weird stuff is doing to any.
Cool down and congeal.
Yeah, it could do lots. It could do lots of things. So it could get up Morkov to find something other spaghetti or whatever. And so the problem here is what we have to do is also infer the final state, and then look to see whether the spaghetti has got the right answer. So we're testing the answer. We're doing a scientific experiment rather than a computation. And in fact, this is what an awful lot of non-standard computing does, is it cherry picks the times when it actually gets the right answer and says, hey, look, it computed an XOR gate, or it computed an adder or whatever. And all the times it didn't kind of work, oh, well, it wasn't set up right. But that's the only way that you could therefore say it was computing it, is because you already knew the answer You had already computed it a different way and were comparing the results. And so that's really a scientific experiment, not a computation. So what would we actually need for a computer? Have I got enough time for this?
Absolutely.
Yeah, okay. So first of all, we need some well-characterized substrate. We need to actually understand how the device works. So with slime mold, do we understand how the device works? Again, this isn't the theory of slime mold. This is just a set of equations off Google. No, we don't have a theory of slime mold in how this actually works. In particular, the domain of applicability. So the shortest path is only a rough approximation and only for small systems. It doesn't scale. And we could see it was a rough approximation because even the picture we looked at had a little bit of slime going off in a slightly different direction. So there's an awful lot of post-processing going on anyway, but it certainly doesn't scale. So there's lots of examples given here. So well-developed systems, so solid-state transistors and classical mechanics, quantum mechanics, and that they're well-known theories, so we can actually use those into design. Reaction diffusion chemistry might be another example of a sufficiently well-known theory that we could use that as the basis. Biological devices rely an awful lot on extrapolation, and they have scaling issues. Even some physical devices do. Again, there's a lot of things said that, particular devices can solve NP-hard problems because, and then someone demonstrates that in the small scale they can solve the problem approximately, but then it doesn't scale. So, for example, there's in fact, this is I believe this is one of Scott's examples talking about soap bubbles finding minimum surface areas, and they do that. But when the system gets big enough, they don't actually find the minimum; they find a local minimum. And in a small enough system, there is only one minimum, and it finds the right one. But in a big system, there's lots and lots of local minima, and so it finds a stationary point, not a minimum point.
But this is even true for your laptop, right? I mean, it doesn't scale arbitrarily.
Yeah.
We kind of pretend that this is a Turing machine with, you can always add more hard disk. But that's not true. It's actually not true.
It's not true.
So what scale are we comfortable with, and what scale are we saying, no, it's too small?
And I think here with the scaling issues, what I'm talking about is people who claim, based on doing small-scale experiments, that therefore it can solve these problems. And yes, it can solve these problems in the small, but that's not the claim that some of these people are making.
I claim that my program for computing factorial will do it for any number, no matter how large, as long as you fix the hardware.
Yeah. Which is not true.
You don't have hardware that's big enough. It's not big. There are all kinds of engineering problems that will pop. So the claim is that you can scale it up arbitrarily are really an abstraction. In reality, you cannot scale up this computer arbitrarily.
Well,
yeah.
Specify the conditions under which it would work.
Possibly a good Q&A arguments to have after lunch. But also in some of the non-standard ones, there's a lot of naive theories going on. The shortest path, they're only approximate theories, a lot of these. And also, in addition, there's a lot of counterfactual theories saying if the laws of Newtonian mechanics were true, then this computer could solve the halting problem. Then you go, yeah, but the laws of Newtonian mechanics aren't true, so you can't physically instantiate it. You can't do the computation in this universe. So you often have, so that's unbounded speeds. You also tend to have these non-atomic things where you can arbitrarily keep dividing time and space, which is also, again, not the way the world works, unfortunately. You also need a well-engineered instantiation. Computers are engineered devices. They might be engineered explicitly by us, or they might be engineered implicitly by evolution, if we can agree that biological systems can compute, and I hope we can agree biological systems can compute, because that's what we do. I go 1 + 1 = 2. I think I'm not a well-characterized theory though, but hopefully I'm a relatively well-engineered instantiation, thanks to evolution. So there's lots of engineering issues in actually building non-standard or even standard devices. So there's lots of work going on. Nowadays, ideas of non-standard computers tend to have very simple components. So there'll be a slime mould and a few oats. But if you think of more sophisticated devices, they have multiple kinds of components. There's interconnection, there's control, and most importantly of all, there's programming. There's getting them to actually do what you want. Things with the slime mould, for example, the programming is setting the oat flakes in the right place. And so there's a lot of work going on in setting the oat flakes in the right place. It's a kind of a one-shot device. And there's lots of issues about scaling, not just extrapolation, but interpolation as well. How do you know that you can actually do the points in between the ones that you've tested? It needs a predefined encoding and decoding, because otherwise you're cheating, you're bringing in something extra from outside the system. So that's why these ones aren't computing, not computing the things they claim to compute. I can maybe compute the identity function with lots of things, okay? And a natural fit to the problem as well, which Aaron certainly might disagree with, but I certainly wouldn't want a slime mould computer computing my tax returns, for example. There are things where slightly noisy, slightly approximate solutions are fine, and there are things where we want to get the answer right to a higher precision. But a natural fit means it would be nice for a system to have the desired abstract dynamics and the actual physical dynamics fitting together well. A small semantic gap, which is actually pretty poor for these classical devices. You kind of have to torture the silicon to get it to implement Boolean logic, which is why they run so hot. Now, I know Aaron's going to say, but once you've got multiple levels of virtual machine, this is irrelevant, but I'm actually thinking in this smaller scale there. Being able to use certain devices for certain tasks. But analog computers, for example, can very often have a much smaller semantic gap, and that's why recently when in the UK, certainly there was a switch from analog to digital radio, and everyone complained that the digital radios drain the batteries faster. That's because of the larger semantic gap. Okay, a bit faster, I thought. Right. So, just to summarise, a well-engineered computer and its program, I'm bundling them all up together. You start with an abstract problem that you want to find the solution to. You program, you potentially build the computer, you program it, you encode the input. It evolves under the laws of physics, and then you decode the output. And the computing is happening in all three of those. And we often forget, certainly that side and that side, when we're trying to calculate things to do with computability and complexity. And in fact, computer science as mathematics tends to sit up here and ignore the fact that the physical world exists, and talk a lot about the kinds of things that you can infer and so on. And that's why sometimes you end up with theoretical counterfactual, counterfactual in physical terms devices. But there's a similar problem with just thinking of computer science as physics. People will just look at this bottom and say, what is the physical system doing, and forgetting the problems with encoding and decoding. And that's where you get some of the missing out what the computational power of these devices is. But actually, if we want to think of computer science as computer science, we have to look at the whole lot. We have to look at the abstract domain, and we have to look at the physical domain. And this abstract domain can have more layers up above here. We tend to have like a refinement stack or virtual machine stacks. That can keep going up, but it's not turtles all the way down. It stops at some point abstractly and has to move into the different physical domain. And that's the bit that I'm talking about here, is this arrow is not a mathematical arrow because it's mapping from a mathematical to a physical domain. Mapping from a model to the actual domain. It's a representation, it's an instantiation. So really what I'm saying here is the full study of computer science needs to include the abstract and the physical. So this work was done with my collaborators. The stuff I've been talking about is in this particular paper. It was published a couple of years ago. And then we've just finished another paper that's to appear, talking about when evolved systems can be considered to be doing computing rather than just doing their thing. Thank you.
Thank you. Well, we've got a Q&A this afternoon, but I think, those who can't be here this afternoon, if there's some questions now. Okay.
Can you go one step back, 43?
That one?
I think I don't like the computation part at the top.
Sorry?
In software engineering, you talk about input-output specifications.
Mm-hmm.
It's not clear that you can do actually computation up there. You can get a specific input, a specific output, and check whether it is compatible with the input-output specs, but it's not really a computation.
Yeah.
For that, you need a computer quite often.
So, well, yes, but that computer can be, you can do a calculation. You don't.
Yeah, the
but
computer is at the bottom.
I haven't said at all what of these are implementable by this process. That's a different.
No, there is no
yeah.
process. This is what I'm saying. There is no process to compute from NP and prime.
So
you
clearly,
can just do a check on
yeah.
both sides when you are given.
Clearly, everything is physical.
Mm-hmm.
Clearly, the abstract domain doesn't exist. Sorry, I'm a physicist. So there is an abstraction going on here, and the thing about where else this is happening gets folded down into some other physical domain. But what I'm trying not to go there first, because that then ends up with too many levels of different physical stuff going on. I'm trying to say, let's say at the moment there's some abstraction here, and we're quite happy in thinking about that there are abstractions. But if we're thinking about that, they have to exist somewhere. Everything is physical. But this is potentially a separate device doing the computation from the computational entity who wants the computation done. I'm not saying the computational entity who wants the computation done is intelligent or conscious or anything like that, but there's a computational entity and there's something computing. They might be in the same thing, or they might be separate. So here I might say the computational entity is the user, and they are obviously implemented in some other physical device, but I don't want to go into that because that causes confusion. It might cause different confusion.
I think what Katril is referring to, that at the upper level are really two views. One, you're thinking in terms of a program. Right? There is a program and you can infer somehow the behavior of that program. But if you think about, for example, computing shortest path, we don't have a program at the higher level. We have a specification.
Yeah.
Here is a graph, here is a mathematical notion of a shortest path, and we are not necessarily even talking, here is an algorithm there, right? It's just a problem.
Yeah. So that's, I've used this word infer. I'm assuming there's some way of getting from there to there, but I'm not at this point saying how that is done, and I'm not at this point saying what the constraints are on what is possible to do there. I'm just saying that's a different topic.
But I don't think you need the infer there. It's enough that you say there is a mathematical mapping.
Yeah,
so
and
there is a mathematical mapping.
So the inference
when you find
would
from
be
a graph and 2 points to it's not even a mapping, a relation between a graph and the shortest path.
So that's the simplest.
That would be actually good enough for your picture. The word infer, I think, is too strong. You don't need infer there.
Well, the inference in that particular case is very simple. The inference is looking it up in the mapping. And so it's a really simple inference. But I didn't want to say that it had to be a mapping. I didn't want to say anything about what it is.
I think the point is, if you put it's a relation, it's a well-defined mathematical relation, I think that would be good enough.
But it is a well-defined relation. Sorry, there was one at the back first, sorry. Sorry, even further in the back.
Okay.
Yeah, but along comes,
I'll start with this question. So in some sense, your claim is that computation is, or computing, not computing. Computation, as I understand it, is an abstract mapping or mathematical mapping or something like this. It's up there.
Yeah.
And
I don't think she said.
Well, I'm trying to say that computation is if you want to make a distinction between computation and computing, one way of doing it is to say computation is that. Is a subset of that, because not all those mappings are.
It's not like you did it. You put it in one of the slides, computation up there, not down.
Yeah.
No, I don't agree. It seems that computing is something that is maybe theory relative or user relative. So for instance, if I take this, your laptop and put it, somewhere else in, some remote planet or something like this, and no one uses it, or someone comes and uses it but knows nothing about computing, just, press buttons and then get all sorts of displays on the screen. So you would say, well, there is no computation at this point. I mean, the laptop doesn't really compute, because there is no...
so the compute isn't just this level.
Right.
It needs a representation and an instantiation.
So, so basically, it's just whether there is an encoding and decoding. This is what makes
Not just, but that's
So
needed as well.
the Zen expression, if a laptop sits in the forest and nobody uses it, doesn't compute
No,
it.
someone uses it. But
the monkeys are typing it
right,
down.
But they're doing a different computation.
But the process is not, so there is no computation going on. Okay.
I would like to add something.
Sorry,
whatever. I'm happy to wait for somebody else.
Okay, let's go with you then.
Well, it was Jonathan.
Okay. I have a clarificatory question. You said that an organism is well engineered as a product of evolution, but we know that a lot of times the product of evolution doesn't really fit the model of your engineering model. Like there's a lot of glitches in the process.
Well, it's it's potentially well engineered to do the specific computations that it's doing. If once you can figure out what computations it's doing, it might not be fully scalable. So, for example, I can add 1 + 1 in my head, but if I wanted to add larger numbers, I would need a slightly larger system, which with a pencil and paper as well. But when I'm saying well engineered, what I'm trying to say is I am not implying that it's only artifacts that we make. That in fact biological systems can compute, and the analog of the engineering is the evolution, which has a slightly different way of making that epsilon smaller, which is just killing off the stuff that didn't work, until at the end you've got a device that is actually well engineered, but lots of scare quotes around the engineering, obviously.
It's not always well engineered. There are some known cases where it's very not well engineered and still doing its stuff.
Yeah. Well engineered, remember I said that the epsilon is sufficiently small for the purposes. I'm not saying it has to be perfect, I'm saying it has to be good enough, and that's what I mean by well engineered. Engineering doesn't make things perfect, it makes things good enough for the purpose that they're there for. And I don't like using words like engineered and purpose around evolution, but that's why I keep doing these scare quotes. But what I'm trying to say is there are biological systems that can compute, and systems not engineered by us.
I wonder if this is a kind of a meta question, that I noticed when you get to the publication stage that there are a number of people involved. I wonder if you could say a little bit about how you work. Perhaps that's too specific a question, but why ask, and this is asked in a very positive way, how does one work with a group of people?
What's your experience?
What is your experience, basically, of how on earth you do it? Because we are wrestling with that with Babbage and Lovelace, you see. How did they work together? What were the specifics of it? And so it's coming from that point of view, and they did, and it worked out, and they had their disagreements.
Yeah.
You know, but I'm interested in how you got to this group.
Right. Okay, so we're in interdisciplinary group. I find it much easier to work in interdisciplinary groups than in disciplinary groups, because the arguments are very different and who's right depends, changes a lot. So Horstman is a philosopher slash physicist slash computer scientist, but mostly a philosopher. Kendon is a physicist, and I'm a computer scientist, well, pretending to be a computer scientist, used to be a physicist. Wagner was a PhD student, has now moved on, and so it's now just the three of us. So how do we work together? We talk a lot. We work on the whiteboard a lot. We argue a lot over drafts of papers. We work on the whiteboard a lot. And I think sometimes it's, when we were starting to write this paper, it was quite interesting that there were a few discussions and Horstman was saying a variety of things, and I couldn't work out what on earth was going on. So I wrote down explicitly what I thought was being said, at which point Horstman and Kendon said, that's not what was being said. And then some progress actually happened. But there's also stuff on the whiteboard and, you know, trying out ideas. There's an initial point of trying to understand each other's terminology, and an initial point of trying to understand what each discipline thinks is a good argument. And it's just quite a lot of work. I mean, it took us 2 years to get from this one to this one. Sorry, this is wrong. There's another author on this, my mistake, Young, who's a biologist. So that got even more interesting at that point, bringing a biologist into the mix. I find interdisciplinary working really interesting because you ask different sorts of questions, or you say something, or you ask a question, the person in the other discipline goes, oh, no one's ever asked that question before. I don't know what the answer is, let's think about it. Because some stuff can just be so implicit that you don't realise it, even that it's an assumption that you're making.
Thank you very much, because I wanted to understand your process, not just your compelling conclusion. Right. So how you got there?
I think it took 2 years to write this paper because of all that that stuff. And that was a combination of getting the answers straight and getting the answers equally straight in everybody's head, in their own language.
Aaron, do you want to keep your question till the after lunch, or?
Well, I think it's quite a short one.
But is the answer short?
Well, I mean, it would take a long time to discuss, but it's an observation that I may have got completely wrong, but it seems to me you haven't mentioned compositionality in a way which is very important, and it makes a huge difference to both what's happening at the top of your screen and at the bottom. And you have to decompose in order to check most complex designs. You can't just look at the inputs and the outputs. I say you agree.
So there's lots more work to do, and that's one of the things that we're working on. There's is actually how you build together particularly different substrates, some doing part of the computation, some doing another part. And what's really interesting, in fact, Horstman's got a paper, single author paper on this, of actually showing in this model, if you've got two different substrates, there's some interesting stuff you can do in the instantiation representation relations that allow you to do composed computations that you can't do by simply composing the inputs and outputs.
And a lot of applied theoretical computer science, if that's not a contradiction, is concerned with methods of decomposition and building model checking systems.
Oh, absolutely. Yeah. So, but all of that takes place up here. There's a lot of stuff that takes place down there, but actually we're saying there's some interesting stuff, compositional stuff that takes place on those branches as well.
And I'll cheat by adding a little anecdote in order to the last thing. I was once in a collaboration where a very interesting thing happened where someone proposed a solution to a problem. I didn't like that solution. I made a counter proposal, and then a third person, was all done by email, wrote to me saying, I like Aaron's proposal. So I wrote to the group saying, I like Aaron's proposal because, And it turned out he misinterpreted what I'd said, and we all agreed that what he thought I'd said was the best thing of all.
Yes.
Who came up with the idea?
Absolutely. Who came up with the idea? That is.
I think basically that does bring us to Lovelace, Babbage, you see, those issues. There are the two of them, that summer of 43, and there are these email-like exchanges. Who is doing what? And what can we reconstruct? Yes. We were not there, you were there at this encounter, so you knew what happened.
The whole is more than the sum of
Absolutely. Why should it be one person doing it? It's, I know I can do things in a group that I can't do alone.
And attributing it to the one. I think that's the base question that I was trying to get to, because I think I heard also from Moshe yesterday this idea that he was dealing with the dean, I won't name which discipline, and he said, you know, he went in there and the dean was basically quite averse to the idea of working across lines. And thought, well, we're self-sufficient here, you know, we do our thing and go away. Did I understand you correctly, Moshe? Yep. So here was an opportunity for collaboration with a very fine mind that is rejected out of hand. We don't do that sort of thing. You know.
We find, so being in an interdisciplinary centre, we find that it has to be a self-selecting bunch. There are people who like working across disciplines, and there are people who don't. And we don't try and make the ones who don't want to work across disciplines work with us, because they don't. They're doing their stuff, and that's absolutely fine. And we're all going, hey, look, there's lots of all this stuff over here. How can we bring them together into something new that we couldn't have done by staying in a single discipline?
On the other hand, I found on your website the quote, "Philosophy is to science as pornography is to sex, easier and cheaper."
It wasn't my quote.
No, you didn't say it.
What was the quote, Diane?
Say it again. Philosophy is to science as pornography is to sex, easier and cheaper.
I don't always put up stuff that I necessarily agree with, just things that I find amusing.
There used to be a fashion for interdisciplinarity, and all kinds of groups were set up, buildings set up. And I came to the conclusion after visiting quite a lot of places that you cannot do interdisciplinarity in buildings, you've got to do it in brains.
Yeah, but it helps to have those brains together in a building.
I mean, you have to make each brain multidisciplinary.
No.
To some extent.
To some extent.
That's right.
And I think it's kind of this T-shape. You have your own discipline in depth, but you have to have enough that you can communicate. But there are some people who say interdisciplinarity has to be one brain doing it all, and that...
No, I didn't mean that.
I mean, one brain can't even cope with one discipline, let alone more than one.
And funding councils can't cope with two.
No, because they always send it off to referees who, let's not go into
In a
that.
serious way, we've been toying with the idea of extrapolating the three-body problem. You see, that if you've got Turing, Babbage, Lovelace, so this is a problem that great minds are wrestled with, Newton, Euler, Lovelace, Babbage, etc., to know, specific end result. And so when you've got those three together, then perhaps you need, Joe postulated this is a kind of a Venn diagram, which has it has an overlap sphere, which would accommodate, you're saying that mind has to do some of that work, and then it has to be adjacent in proximity to that other, so that the other can have input to your complex system. Is the way we're trying to...
Yeah, I remember having a discussion with an immunologist, because there's a lot of computational immunology going on as well, and he said, the quote was, "I really love working with computer scientists because you ask such different questions, all of which are impossible to answer."
So should we break?
So
yes. Let's have interdisciplinary minds over lunch. Lunch won't actually be available till